Okay, welcome in presence and online. It is a pleasure for us, of course, today that our Elenia Pacetti will illustrate her thesis work. She got a special mention at the Pietro Tacchini Prize of the Italian Astronomical Society, the last edition, a couple of weeks ago. And she completed the thesis. She defended the thesis in December last year, and she has been active already from almost the beginning of her thesis in a number of collaboration where the work that she has developed has already received a lot of visibility and is already being used by a number of groups to interpret exoplanetary atmospheric data. So the work she did is to do models of how the formation and migration of planets in a protoplanetary disk inherits the composition of the native disk, and how this is influenced by the type of migration that the planet had, and the distance with respect to the star where the formation started. So fortunately, it's not in the motivation for the prize. They wrote that this was an important study for espianti instead of exoplanets, of esopianeti. So fortunately, this is not going to be a seminar of medicina legale. It's much better than that. Okay, so let's hear Elenia.
Okay, so thank you, Sergio, for this very nice introduction. So as Sergio said, this seminar will be mostly about my PhD thesis. Which is really an example of interdisciplinary work. So I think we can and we should spend at least the first 10 minutes trying to put things in context. So let's start from the title. The multifaceted connection between the atmospheric composition of giant planets and their native disk. So we are talking about planets and in particular giant planets. So it doesn't work. Okay. So I think most of you know very well that we have found more than 5,000 exoplanets so far. And the interesting things about exoplanets is that most of the exoplanets that we found they are anything like the planets that we have in our own solar system. So we found objects and architectures that are very different from the ones that we have in our solar system. Here I overplotted the planets in our solar system in this plot with the currently known population of exoplanets. And in these populations, there are some classes of exoplanets that are particularly interesting. One example is the class of hot and warm Jupiters. So these planets are interesting because they are giant planets. So they are planets that are they have the same mass as Jupiter or even bigger, but they are orbiting the star extremely. They are extremely close to their star, so fraction of astronomical units. And these planets are interesting for at least two reasons. One is that they pose great challenges to current planet formation theories, essentially because it's not particularly easy to form giant planets in situ at such close distances, nor via gravitational instability, nor via core accretion. And so these planets are the reason why it has been proposed that planets can actually migrate in this. So they can form elsewhere, so far from the star, and then migrate inwards to their current orbit. And the second reason why they are so interesting is because since they are so big and so close to the star, They have these very hot and extended atmospheres, which make them the perfect targets for exoplanet radiation. So, and this is why they are the main targets of current ground-based, but also space-based missions, and they will be the main targets of the next ESA mission Ariel. And they will be the focus of the first part of this presentation. So context part 2. So how do we, because here the point is that given that we are starting to characterize the atmospheres of these planets, the idea is to use the composition of the atmosphere to get information on how these planets formed. But how do we link the composition of the atmosphere to the planet formation history? So we know that planets form in protoplanetary disks, which are these disks of gas and solids and dust around newborn stars. And our current understanding of giant planet formation is that they form in this multi-stage process. So starting with the formation of a core and then the accretion of a gaseous envelope until the envelope becomes massive enough so that gravity cannot sustain the gas pressure anymore. So we have this phase of runaway gas accretion, in which the planet accretes most of these gaseous envelope until the planets open a gap in the disk. And in this process, planets can migrate in disks. And this is the key point, because in this process, they can interact with different compositional regions in protoplanetary disks, because these do not have the same composition at all distances from the star, because chemistry is driven by 3 main parameters, which are density, temperature, and accretion rate. And these 3 quantities change with the distance from the star. So in this, we have radial profiles of temperature, density, and ionization rates, which result in different compositions of different from the star. And so the idea is that while planets migrate, they accrete gas and solids with different compositions, and this process leave a signature in the atmosphere. And so there have been a number of efforts devoted to developing an interpretative framework that can link the composition of planetary atmospheres to the formation history. And this work is one of them. So where we started, so in the exoplanet community, the first efforts in trying to connect atmospheres to formation were based on this very pioneering work of Karin Oberg in 2011, in which they considered disks as made of mainly 3 carriers. So they considered the composition of disks based on the composition of the most abundant volatile carriers observed in protoplanetary disks, so water, CO2, and CO. And considering the condensation behavior of these molecules, so the condensation and evaporation at different distances from the star, they built these radial variations, this plot, which shows the radial variations of the carbon over oxygen in the disk, in the gas phase, and in the solid phase. And they argued that we can compare the carbon over oxygen ratio in the disk with the carbon over oxygen ratio in the atmosphere to try to identify possible planet formation regions. But this was more than 10 years ago. And reality is actually much more complicated for at least 4 reasons. The first one is that the plot that I showed before was based only, considered disks as made on only of volatiles, and in particular, mostly of those 3 molecules. But actually, in protoplanetary disks, we have that chemical species, we have multiple components. We don't have only volatiles, but we can have refractory material and also components that show intermediate behavior, like semi-refractory, semi-volatile reservoirs. So if we really want to build a model connecting planetary atmospheres to disks, we need to implement a more realistic compositional model for the disk. Then the composition, that disks are not static, because as I told you, if you remember, chemistry is driven by 3 parameters: density, temperature, and ionization rate, but these quantities change over time as the disk evolves. So we have the composition of the disk change over time as the physical structure. And then planet formation itself is not, it's a multi-stage process in which does not necessarily take place in situ. We can have migration, but most importantly, we have that gas and solids are not accreted with the same efficiency during the planet formation process. And so we really need to account for all this complexity in our models. And so the goal of this project was exactly to establish a modeling framework that can link the planetary atmospheres to the formation history using a more realistic and consistent model of the planet formation environment and the planet formation process itself. And we developed this framework within the EcoGround project, the ERC project of which Sergio is one of the PIs, but also as part of the scientific activities in preparation for the aerial mission. So this brings me to the end of this introduction and to the first part of this work, in which, so we started by considering, let's call it stationary disk, in the sense that we assumed for the first part of this work that chemistry in disks evolves up to a certain point, and then we start planet formation. So in the first part of this work, we consider the stationary disk in the sense that the disk does not evolve during planet formation. And so we started with the first challenge that I mentioned before. So building a more realistic computational model of the disk. So we put our focus on 4 chemical elements. So oxygen, carbon, nitrogen, and sulfur. So we extended the set, the original set of carbon and oxygen, including also nitrogen and sulfur. And we combined information from the solar system and other astrophysical sources to partition these 4 elements into different reservoirs in disks. And if we consider the constraints that we can get from meteorites in the solar system, but also from the ISM, we have that we find that actually 50% of carbon is sequestered into refractories, while actually 70% of carbon is in the form of refractories, of which 60%, we have evidence that 60% of it is in the form of a semi-volatile refractory component, most likely refractory organics, because we see only about 9%-ish of carbon in meteorites in the solar system. And then we have nitrogen and sulfur, which have opposite behaviors, because nitrogen is a very volatile element. So it's 90% of it is found in the form of molecular nitrogen, so in the gas phase. While sulfur, we have evidence that as a good approximation, we can consider it to be entirely in the refractory component. And so if we try to update the original plot by Karin Oberg in 2011 that I showed before, which is this one, including also these new inputs from solar system and astrophysical sources, you see that the trend of the C/ρ ratio in the gas phase is no longer a monotonic trend as before. So we updating the compositional models really introduce a sort of degeneracy in the C/ρ ratio of disks. But this is only about refractories. Actually, the equation is complicated also for volatiles, because we don't have only those three molecules that I was showing before. For the volatiles, we consider the astrochemical models by Christian Astrup in 2016, in which they evolved the chemistry using a full chemical kinetics, because the plot of Karin Orbeck, so that compositional model was based only on sublimation and evaporation processes, but actually chemistry in this is more complex. You can have chemical reactions in the gas phase on the surface of grains, and this is very important because we see molecules in protoplanetary disks that can only form on the surface of grains. One example is methane, and so we need to include all the complexity of chemistry. And so we consider the results of the astrochemical models by Astrup, and we use the same for chemical scenarios that they analyzed. So they considered two scenarios. So disks that inherited the composition from the prestellar phase, and disks that somehow experienced strong heating events, and so they reset the chemistry. So from a practical point of view, the two evolutions were run with different initial conditions. In one case, you start with molecular initial abundances, then in the other case, you start with atomic initial abundances, so the chemistry is more active, and then they consider different ionization levels. And so you really see that these are the abundance profiles of the most of the key volatile carriers in disks, which includes also other molecules, in addition to the others that were originally assumed, in which we also include the component of refractory organic carbon. And you see that when you, so this is the inheritance scenario with low ionization. When you increase the chemical complexity, when you start from atomic initial abundances, you increase the ionization rate, the abundance profiles becomes more complex. And so we coupled this compositional model with our planet formation simulations, using simulations developed in our group by Diego Turbini. So this is basically an n-body code that simulates the mass growth and radius evolution of a giant planet in the core accretion scenario, as I was explaining in the introduction. And so they simulates the interaction between the planet and a swarm of planetesimals, and we have gas and solids accretion, and so we can actually trace the accreted masses of gas and solids at each distances during the planet migration and the formation history. So this is an example, a snapshot of the interaction of the forming giant planets with the swarm of planetesimals, which get excited by the interactions with the planet, and they change their eccentricity. This is a flow chart of what we did in this first part. So basically, we post-processed the accreted masses of gas and solids resulting from the n-body simulations with a compositional model of disk, and we decomposed these accreted masses into contributions to the four elemental tracers, so carbon, nitrogen, oxygen, and sulfur, and we use them to compute these elemental ratios in the atmosphere, which in the end are the initial conditions in the atmosphere of planets at the end of their formation process, and they are the starting point to build the observables for the atmospheric characterization. So this is what we found. We considered six different formation histories. So we put the planetary seeds at different distances from the star, covering typical formation regions which are observed in planet-forming environments. And these are all planets that become soft Jupiters. So they end the formation at 0.4 astronomical units. So each point is one of the 6 migration scenarios. And this plot refers to planets that accreted only gas, while this is the case for planets that accreted a mixture of gas and solids. And these are the elemental ratios that we found with our analysis. And these are all elemental ratios which are normalized to the stellar reference to facilitate the comparison. And these are the same elemental ratios, but in the disk. So one first message from this plot is that there is not actually one-to-one connection between the composition of planets and the disk. And this is essentially due to the fact that gas and solids are not accreted with the same efficiency at all stages during the planet formation. One example is, for example, the Azoveran ratio, which for these planets that experience very large-scale migration, it resembles the Azoveran ratio of the solid phase of the disk, because these are planets that encounters a lot of planetesimals, so they accrete. So the contribution of planetesimals is planetesimals to the planetary metallicity is dominates over the contribution of gas, and so the Azoveran ratio in the planet is similar to the Azoveran ratio of the solid phase of the disk. But this is not the case for planets that migrate for short distances, because they encounter less planetesimals. So the contribution of the accreted gas dominates. And you can see that because the Azoveran ratio of these planets becomes substellar, and this is due to the contribution of the accretion of nitrogen, which mostly comes from the gas phase, because nitrogen is a very volatile element. And in fact, you can see this very different. It is very different from the Azoveran ratio in the disk. But this is just an example with this is the inheritance law. But as I said, we consider different chemical scenarios for the disk. So this is these are the same results for all the chemical scenarios and for different elemental ratios. Just to show you that including nitrogen and sulfur, so extending the set beyond the carbon and oxygen, allows us to identify more tracers of planet formation, because if we limit the analysis only to the carbon over oxygen ratio, you see that all the planet formation scenarios, they are close to the stellar value. So the C overall ratio should be very flat profiles. But if we include other ratios in the analysis, so ratios computed with elements with different volatility, this is the key point, that we are comparing elements that condense at different distances from the star, like C and nitrogen. We can have that, we can use the elemental ratios to constrain other aspects of planet formation. For example, here we can use C over N, but also N over O, to distinguish between planets that accreted gas and planetesimals from planets that accreted only gas. We can use the S over N to trace the planetesimal accretion, because the S over N increases with the planetesimals accreted, so with the contribution of accreted solids. And we noted that regardless of the chemical scenarios, so in all chemical scenarios we find that gas dominated are characterized by this relation, while solid enriched giant planets are characterized by exactly the opposite relation. And this is very independently of the initial chemical assumptions. It's a first very strong results. Then this is again another way to show the results in these we call them binary plots. It's a plot that we put in the first paper from 2 years ago, where you see all the scenarios that we analyzed in these plots, which we compare the elemental ratios, and you see which are all again normalized to the stellar reference. which is one. And you see that different different formation scenarios. So the blue dots are for planets that accrete only gas, while the red dots are for planets that accrete gas and planetesimals. And the increasing size of markers traces the migration distance. And you see that they tend to occupy different quadrants in these plots. So this plot is the original one that is present in my paper, but it was recently updated by Giulia Perotti and others for inclusion into a review. This is exactly the same plot, but with all the information condensed. This is the case of CORN and CORO, where you can clearly see how the different planet formation scenarios are distributed in different areas of this plot, which we can use to constrain different planet formation histories. So this was the first part. As I said in my introduction, disks are not static. Most of my PhD thesis was actually dedicated to the development of this code, JADE, which is a code that simulates the integrated physical and chemical evolution of the disk. So we now shift our attention to the planet formation environment, because our goal is to have a more realistic description of what happens in the disk during planet formation. Because, as I said before, chemistry in this is more complicated. We have reactions that can occur in the gas phase and the surface of grains, as well as interactions between gas and grains. And in these disks, we have gas and solids, which are not static when they evolve. The gas in disks mainly evolves through viscous evolution, while the dust, depending on the grain size, can experience radial drift. And so, because again, the gas evolves, the temperature evolves, and also the ionization rate, so the chemistry evolves, and these are all processes that are interconnected. And so in the second part of my thesis, we developed this code that at the moment includes the effects that I highlighted here. So this is a scheme of the code. As I said, it simulates the integrated physical and chemical evolution of the disk in an operator splitting scheme. So we have a first module that implement a full chemical kinetics to model the evolution of the abundances of molecules, in considering a full set of chemical reactions. And we couple this chemical evolution with a physical model that includes viscous evolution, the dynamical evolution of the dust coupled to the gas, and also the turbulent mixing. So we also allow mass exchange between neighboring cells. So this is one example. So the first application of JADE was to evolve the disk that we used in the first paper. So we started with a disk very similar to the one of the first paper in terms of surface density and temperature profiles. And this is assuming an initial dust to gas ratio of 0.1, and this is the surface density of the gas, while this curve is the surface density of the dust. At the moment, we can only model one single grain size, and so we can really appreciate the differences between physical evolution of disks with different grain sizes. So this is a disk with grains of the submicron size, which is a typical size of grains in the interstellar medium. And then we modeled two other scenarios with larger grains, up to 100 microns. These grains are all below the typical size of pebbles assumed in this. So we are actually talking about small grains, but these are grains that we actually see in protoplanetary disks. So we have observations for them. We have evidence of the existence. And so you see that the coupling, the dynamical evolution of grains in disks depends on how strongly they are coupled with the gas. So small grains are very strongly coupled with the gas, which means that they tend to follow the gas in its viscous evolution. So over time, you see that, well, this is a disk that has a viscous time scale of 10 mega years, and we performed our simulations for 3 million years. So you cannot really appreciate a strong evolution of the surface density of the gas. But in this scenario, you see that the dust is following the gas in its evolution. While if you increase the grain size, you have the coupling with the dust weakens. So you have the dust experience a radial drift. So you see that over time, the dust accumulates inwards towards the start. So how does this impact the chemistry? These are the abundance profiles in one of the 4 chemical scenarios that we considered. In particular, this is the research one, but we did the same for all the other chemical scenarios. And you see the difference between how the drift, the radial drift impacts the molecular composition of the disk. You see that we increasing the size, the grain size, you have this drift of dust, and what happens is that when the icy grains cross the snow lines in the disk, they release their volatile content back into the gas phase, and you can clearly see it here. So you see the gas phase that over time, well, these are the results at the end of the simulation, so 3 million years. And you see that the gas phase is enriched because of the sublimation of the icy mantles. So these are for the molecular species. But if we see what happens to single elements, this is the gas phase, and this is the carbon in the gas over time and at different distances from the star. And so you see that the scales are different, but for large grains, you can clearly see that we have this region, which is significantly enriched compared to the other scenarios in carbon, which is the carbon that has been released by the sublimation of the icy grains. And this effect is expected to have a strong impact on the atmospheres of planets, especially planets that start their runaway gas accretion phase in these regions. So I don't know if you can see them, but these are the migration tracks of the 6 migration tracks of the simulations, the same simulations from the first paper. And this dot is the onset of the runaway gas accretion phase. So the expected effect is that these planets, which start the runaway in this region, they will accrete gas, which will be enriched in heavy elements because of this sublimation effect. So these planets are expected to have high metallicity in the atmosphere, but not because they accreted solids, but because they accreted gas enriched in heavy elements. So don't be scared by this plot. This is just a way to show all the results of all the scenarios that we considered. So just for orientation, each colors is one of the 4 chemical scenarios that we considered. So inheritance and reset. I know the labels are too small, but so each curve is the time evolution of the elemental ratios in different scenarios. So the colors are for the chemical scenarios, while the markers are for the grain sizes. So each dot each point on each curve is a snapshot at a given time, while the blue dots are the results at 1 million years. Just to say that if you consider the entire evolution of the disk, we have that the elemental ratios, they can show a very different time evolution. Because the point is that when we observe disks, it is difficult to assess how old they are, so at which stage of the evolution we are. And the other thing is that actually we don't observe, we cannot always resolve disks at very small scales. So we have access to large regions. So we also try to see how our results are distributed in different regions in the disk. So here we divided the disk in 4 regions, 4 representative regions. So the region 1 is the region within the dust sublimation radius. So where you don't have all the volatile species are, but this region is too hot to have volatile in the ice phase. While region 2 is the regions where most of the snow lines fall. And then we have a transition region. So just for reference, this is the regions where in the solar system we have all the giant planets. We currently have all the giant planets, while this region is a transition region, and while this region is the very outer disk where the molecules with the lower volatility condense, like for example CH4, O2, N2, which is a very ultra volatile molecule. And so analyzing our results in these 4 regions, we found that actually there are some regions which can be used to constrain different aspects of planet formation environment. So the first region is it's a bit of a mess, but if we focus on other regions where we have most of the snow lines, we can start to distinguish disks where we have chemistry inherited from the crystalline phase, from disks where we experience a reset of the chemistry. In region 4, we also might have the chance to distinguish between the ionization level. So these are the scenarios with high ionization, while these are the scenarios with low ionization. And in some regions, for example, in region 3, we can also use one single ratio, like the C/ρ ratio, to distinguish between different chemical scenarios. And so this kind of analysis offered a new perspective into our results. But this was for the disk. So we coupled these results with, again, the same planet formation simulations from the first paper. So here this is the same results that I showed before. So the stationary disk, while these are the results with the time-dependent model. This is the case for the inheritance scenario with very small grains, which are very well coupled to the gas. So you don't see a lot of differences, because in this case, if you have very small grains, and particularly with the disk that we considered with a very long viscous time scale, as long as we are in a disk that inherited its composition from the crystalline phase, and we have small grains, we don't see a lot of differences between the 2 cases. But this is not the case if we increase the grain size. There is a typo here. So this is not 0.1, this is 100 micron. So these are the scenarios with the largest grains, where you see that the elemental ratios start to deviate, and especially in the inner disk, which is the region of the disk that is most largely affected by the sublimation effect. You see that the ratio assume different. They follow a different trend. And if we consider the different chemical scenarios, what we found is that actually disk evolution, so including the evolution into our model, highlighted a new class of planets that were not that could not be modeled before with a stationary disk, which are these sub-dimension dominated giant planets, which are this green area here. So these are the results with 0.1 micron, and this is with large grains. So these are, as I was saying before, these are planets that accreted gas that was enriched in heavy elements. So it means that they show the same signatures as planetesimals dominated planets. So C over N larger than C over rho and larger than N over rho, because they have very high metallicity atmosphere. But the reason, what changes is the cause of this enrichment, because in one case it was planetesimals, and in the other case it's the gas. So these planets can be distinguished from the others looking at the S over N, but here S over N is just a proxy for a more generally a refractory to volatile ratio. So we can actually use any other refractory elements that we might have access to in the atmosphere in place of sulfur and have exactly the same results. Here the point is that these planets will have a small refractory to volatile ratio because they accreted gas enriched in heavy elements. And this is an update of the plots, of the binary plots that I showed before, where the inclusion of this new class highlighted a new region in the plot that was not populated by the results of the stationary model, but they now include planets that the sublimation dominated planets. So this is the end of the second part. This is what we did during my PhD thesis, and as Sergio was saying, we really had the chance to apply this framework that we developed to a number of observational applications, starting from exoplanetary systems. So we have, how much time do I still have?
Fine.
Okay. So this is a work that we did in collaboration with people from the GAPS program at the TNG telescopes. These are the observed planets with high resolution spectroscopy. In particular, Veloria and Ilaria, they managed to constrain C over rho ratio in the atmosphere of was 6 planets, I remember well. While Katja, in her work, characterized the stellar composition of these systems. And so we had the chance to apply our framework to the interpretation of these 6 planets. But these first works were mostly based on carbon and oxygen. So we had access to C over rho. Now, thanks to JWST, we're starting to see also some nitrogen and sulfur-bearing species. So hopefully we will be able to perform to really exploit our modeling framework that includes also these elements. And then we also had some works that used third-party works. They used our methodology, particularly Peleki and Wang. They do a similar work as Katja. So comparing elemental ratios in the in stars, in planets, and in their host star. There is also crossfield. We use our models to make a comparison and try to distinguish between planetesimals accretion models like ours and pebble accretion models. Which is a work that we are actually also doing in our work. People at Torino, sorry, in our group, people at Torino with Diego are also working on pebble, on extending our model to include also pebble accretion. And this is the work by Danai Policroni. Then of course, we cannot forget our planets in our solar system, because our methodology is actually particularly versatile. So the model that we built, it was applied to extrasolar system, but it can also apply to planets in our solar system. And so we made this work in collaboration with people in the Juno team, which is about to be submitted, I think by the end of this week. In which we considered the observational constraints that we have from Galileo and Juno on the metallicity of Jupiter and and nitrogen and sulfur. And so combining these, we analyzed 260 planet formation simulations with our model, considering different planet formation, migration, and also mixing in the envelope of the planet, trying to reproduce the observational constraints from Galileo and Juno. So this is the density matrix in which, in yellow, you can see all the scenarios that are excluded by our analysis. And so we are left with a region in this plot. So on the y-axis, we have the degree of mixing in the atmosphere. So one is atmosphere which are fully mixed with the interior, while these are the formation scenarios, the six migration distances. And this is a reference for the snow line of N2. And so in this work we found that our scenarios are consistent with Jupiter that formed beyond the snow line of molecular nitrogen, but with a high degree of interior mixing. So this was the first application that we did to Jupiter, but there are plans for extension to the other giant planets in the solar system. And in particular, we are participating in the next MESA-Orion flagship mission, which is starting now this year. So we will apply this methodology to Uranus, but also Neptune. So just the two last slides. Okay. So since with our model we managed to include also refractories. So in addition to volatiles, which are the focus of virtually all the models in planet formation, we also include the refractories. Refractories, they can have a significant impact in planetary atmospheres, because our models, my models, they stop at the primordial composition of the atmosphere, but then the atmosphere can be processed over time. So you can have chemical reactions in the atmosphere itself. So we provide only the initial conditions, but then our elemental ratios must be coupled with atmospheric chemical model. And if you have refractories in the atmosphere, what we found is that already using simple equilibrium chemistry in the atmosphere, this is a work by Sergio, which is here today, we found that depending on the temperature that you have in the atmosphere, you can have that oxygen binds to refractory species. And this might be a problem because we cannot observe refractory species in the atmosphere. The C/O ratio in planetary atmospheres is constrained with water and CO in the atmosphere, so gas phase. And so if we have that refractories can bind that oxygen can bind to refractory elements, we will be subtracted from the gas phase. And so this might introduce a bias into our estimations of C/O ratio. And so we quantified, with Sergio, this bias in the estimates of C/O ratios, which we called the oxygen deficit. And now there are new results which are close to submissions, where Sergio again explored how this picture changed if we consider the full set of our chemical scenarios, because this first work was based only on the inheritance scenario. And then we have other people in our group, in particular Paolo Simonetti from IAPS, which is who is also exploring the impact of disequilibrium chemistry in the same context. So last slide. So we also, as I said, this was a work that was done within the as part of the activities of the in preparation to Ariel. Actually, our group is coordinating the planet formation working group in the science team of Ariel. And there is this effort, this exercise that we are starting to do now, because we are assuming we are in collaboration with all the working groups in the Ariel science team. We are testing all the pipeline, all the tools that we have as if Ariel were due to launch in 2025 instead of 2029, to see if we are ready to do science with Ariel. So the idea is that we have this large synergy with all the working groups. We get inputs from stellar characterization, working groups into our planet formation and planet environment models. Then we send our results to the atmospheric chemistry working group, which they send the results to the spectral retrieval working group. So the goal is to see if, given the Ariel spectra, we can do retrieval and we can constrain planet formation scenarios that result from our model. So in our group, we started topical sub-working group because we realized that there is really a lot to do in each of these blocks, and in particular in the planet formation, in the planet forming environment. And I'm the contact person of the sub-working group dedicated to this and this evolution. And this activities has also recently received support from two large computational programs at Pleiade and Leonardo. And I stop here.
Thank you very much. Thank you very much, Elenia. Nice overview of all the work, impressive work that you did during your thesis. So we can start with the questions. I don't know if Evgeny, you can monitor the situation from online attendance. So are there questions for Elenia?
So, thank you, Elenia. Very nice talk. As you know, I'm not an expert on this topic, so it may be a stupid question, but can you go back to the slide 17? I have a comment that drives me a question, actually more for Diego than for you, but this scenario says, yes. So the curve that you show in the lower plots are the migration to set the planets, right? The dotted curve that you show, the white curves that you show in the plots there are the tracks, let's say, yes.
Mm-hmm.
So first I was expecting the migration being larger, if I remember. I was expecting a much larger migration, say.
It is. I mean,
This is in log space.
Yes.
yeah,
100 astronomical units.
Yes.
This is
lot.
5, 19, 50.
So the migration is not to be read this way.
This is the time, but
That is time.
no, but okay, maybe I got this because during migration, it's not. You have different time scales. So
Yes.
stage process, you have a first phase where the planet migrate for a shorter distance, but then you see the end of migration is here. Going forward. So you have a first phase.
And then
by
they track
March.
in this
Yeah.
way. Sorry, okay, I missed the horizontal part.
Yeah.
Okay.
This is.
I thought it was
this
just
is
a
after
vertical.
the runaway gas fission, and then the planet.
Okay, no, that's much more clear.
Yes.
I missed that part. So following this, the question related to that is, does migration tracks they change also with the chemical composition of the core, I guess. Has been developed this kind of changing migration or those
You're
migration are the
talking
same?
about the feedback of
Yes.
chemistry,
Yes,
that we
Uh,
don't have this at the moment. We are.
exactly. I think you don't have yet.
No, no, we are not.
Do you have an idea if it may have an impact or not? I guess it's yes, but I don't know
I
how
think
much.
more than chemistry, I think you are talking about how the gas distribution
Yes.
change and how this impact uh, the migration, because of course migration is due to the interaction of planets with just due to the gas drag, so it depends on the distribution of gas. We actually have this in plan, this interaction with essentially jade and mercury, which are the body simulations by Diego. So we do that. It's also very computational.
Oh, okay.
Intense.